let's just dive right into this explainer. Look around you. We're constantly surrounded by everyday chemical crime scenes. Think about it. You leave milk out on a hot summer day, and it sours. An iron pan sits in the humidity and slowly rusts. Or, hey, even the food you literally just ate is digesting in your body right now. In all of these situations, the original substance has completely, fundamentally changed. These aren't just minor physical shifts, They are actual, real-time chemical reactions.
And that brings us to this great quote from Martin H. Fisher. He says, "Facts are not science, as the dictionary is not literature." I love this because it perfectly sets up what we're doing today. We aren't here to just memorize a boring list of disconnected facts. Instead, we're really learning the grammar and vocabulary of the universe itself, figuring out exactly how elements interact, combine, and break apart to create everything we see. So today, we're deciphering the language of chemistry. We're going to take the seemingly invisible magic of chemical reactions and transform it into a structured, decipherable language. By the time we wrap up, you'll be reading chemical equations like sentences in a book. Here's our quick roadmap. We'll start with the clues of chemical change, move on to the language of chemistry, figure out the balancing act, explore combination reactions where things come together, and finally, look at decomposition reactions where things break apart. Let's get into it.
Part 1. Clues of chemical change.
So how do we actually know a chemical reaction has happened? Because obviously we can't see individual atoms rearranging themselves, we need physical evidence. And luckily, chemical reactions leave clues. There are 4 main indicators: a change in state, a change in color, the evolution of a gas, or a change in temperature. Like if you burn a strip of magnesium, it erupts into this blinding white flame and leaves behind a white powder. Or if you drop zinc into some dilute acid, you'll immediately see bubbles of hydrogen gas, and the container will actually get warm to the touch. These are literally the universe flashing a neon sign saying, hey, a chemical reaction just happened here.
Moving on to part 2, the language of chemistry. Once we spot those physical clues, we have to document them. But writing out full sentences every single time is, frankly, tedious. We need a shorthand. Looking here on the left, we have a basic word equation. Magnesium plus oxygen yields magnesium oxide. It gets the job done, sure, but it's clunky. Now look on the right. This is the true language of chemistry. By using chemical formulas instead of words, Mg plus O2 yields MgO, we get a concise, elegant shorthand. The substance is changing. Magnesium and oxygen are our reactants on the left. The brand new substance, magnesium oxide, is our product on the right. And that arrow in the middle, it just shows the direction of the change.
Part 3. The balancing act.
Now we have our neat little shorthand, but it's absolutely not a free-for-all. This shorthand has to obey the ultimate unbreakable rule of the universe, the law of conservation of mass. Mass can neither be created nor destroyed. Think about what that practically means for equations. Atoms do not magically vanish into thin air, and they definitely don't pop into existence out of nowhere. The total mass of the elements in the reactants has to perfectly match the products. Bottom line, the number of atoms of each element must remain exactly the same before and after the reaction. Let's see how this plays out. Imagine reacting iron with water to get magnetic iron oxide and hydrogen gas. The basic skeletal equation is Fe plus H2O yields Fe3O4 plus H2, but look closely at this table. On the left side, the reactants, we have 1 iron atom, 2 hydrogens, and 1 oxygen. But on the right side, the products, we suddenly have 3 irons, 2 hydrogens, and 4 oxygens. See the problem? This is an unbalanced or skeletal chemical equation. The mass is out of whack. We have to fix this. To fix it, we use a super straightforward approach called the hit and trial method. Step 1, drop boxes around each formula. Why? Because you absolutely cannot change anything inside those boxes. You never mess with the actual chemical formulas. Step 2, start balancing with the compound that has the most atoms. Here, that's the Fe3O4. From there, we just make trials, putting whole numbers, coefficients, in front of the boxes until the left side perfectly matches the right. So we need 4 oxygens on the left, so we drop a 4 in front of the H2O. That gives us 8 hydrogens, so we counter by putting a 4 in front of the H2 on the right. Finally, we need 3 irons on the left, so a 3 goes in front of the Fe. And boom, 3Fe plus 4H2O yields Fe3O4 plus 4H2. The scales are perfectly balanced. To take this balanced equation to the next level, we add tiny physical state symbols. We use an S for solid, L for liquid, G for gas, and AQ for aqueous, which just means dissolved in water. So our iron equation officially becomes 3FeS plus 4H2OG yields Fe3O4S plus 4H2G. Notice that little G next to the water? That one tiny letter tells us that in this specific reaction, the water is actually in the form of steam. It's wild how much data is packed into just one line of text.
Let's jump into part 4, coming together with combination reactions. Now that we're fluent in writing and balancing, let's look at our first chemical archetype. A combination reaction is exactly what it sounds like. Two or more substances fuse together to make one single new product. Like burning coal, right? Carbon and oxygen combine to form carbon dioxide. But this stuff isn't just happening in a lab. Here's a crazy thought. Did you know your own breathing is a combination reaction? It sounds like magic, but staying alive right now relies entirely on this specific chemical reaction firing off inside your cells. We all need energy to survive, obviously, and we get it from food. During digestion, carbs break down into simpler things like glucose. Then inside our cells, that glucose combines with oxygen. Looking at our equation, C6H12O6, that's the glucose, plus 6O2 yields 6CO2 plus 6H2O plus energy. This is an exothermic reaction, which is just a fancy way of saying it releases heat or energy along with the products. That energy popping out on the right side of the equation, that is literally what powers your entire body. Finally, part 5, breaking apart with decomposition reactions. So if combination is all about fusing things together, decomposition is the exact opposite. It's about stressing a single reactant until it breaks down into simpler products. Stable molecules don't usually just fall apart on their own, you know? They need an external force to shatter those chemical bonds. There are a few main triggers here. We've got heat, known as thermal decomposition. Think heating limestone until it breaks down into quicklime for making cement. We can also use electricity. You can pass a current through water to literally split it apart into hydrogen and oxygen gases. Or, honestly, even just sunlight can do the trick. Leave some white silver chloride out in the sun, and the light energy decomposes it right into gray silver metal and chlorine gas. I'm going to leave you with one final thought to chew on. Next time you see a building with fresh, shiny, whitewashed walls, ask yourself, what invisible chemical reactions are happening right in front of me? Because when those walls get painted, they're coated with slaked lime or calcium hydroxide. Over a couple of days, that calcium hydroxide is slowly reacting with invisible carbon dioxide in the air to form a thin, hard layer of solid calcium carbonate. That is the exact same chemical makeup as marble, and that's what gives it the shine. I hope this explainer showed you that the secret language of chemistry isn't just stuck in some textbook. It's being spoken absolutely everywhere, every single day. Thanks for hanging out, and keep your eyes peeled for the chemical world around you.